NASA, a leader in space exploration and scientific discovery, has once again captivated the world with its latest revelation: a new planet exhibiting lights that appear to be artificial. This groundbreaking discovery raises profound questions about our understanding of the universe. Are we on the cusp of unraveling cosmic secrets that could transform our knowledge of the cosmos? Could this new finding suggest the presence of extraterrestrial life? Join us as we delve into NASA's fascinating findings and explore the potential implications of these extraordinary lights. In 2007, NASA launched the Dawn spacecraft with the ambitious goal of exploring some of the most intriguing objects in our solar system. The mission was designed to investigate Vesta and Ceres, two of the largest and most enigmatic bodies in the asteroid belt. Dawn's journey marked a significant advancement in space exploration technology, thanks to its innovative ion propulsion system. This advanced propulsion method allowed the spacecraft to undertake a mission of unprecedented scope and duration. The Dawn spacecraft was equipped with 3 ion engines, which were pivotal in achieving its mission objectives. Unlike traditional chemical rockets, ion engines provide a continuous, gentle thrust that enables spacecraft to travel vast distances efficiently. This propulsion technology was crucial for Dawn's journey, allowing it to conduct complex maneuvers and reach its destinations with precision. Dawn's mission began with a 14-month survey of Vesta, the second-largest asteroid in the asteroid belt. Vesta, with its diverse geological history and complex surface features, offered a wealth of scientific opportunities. During this period, Dawn sent back a wealth of detailed images and data, revealing Vesta's intricate surface and providing insights into its formation and evolution. The spacecraft's observations highlighted Vesta's unique characteristics, including its large craters, mountain ranges, and extensive troughs. Upon completing its mission at Vesta, Dawn embarked on the second and most anticipated phase of its journey: a detailed study of Ceres. The transition from Vesta to Ceres was a remarkable achievement, facilitated by the spacecraft's ion engines. These engines allowed Dawn to exit Vesta's orbit and set a course for Ceres, a feat that traditional chemical propulsion methods would have found challenging. The ion engines provided continuous, gentle thrust, enabling Dawn to cover the vast distance between the two celestial bodies and enter into a stable orbit around Ceres. Ceres, discovered in 1801 by Italian astronomer Giuseppe Piazzi, is the largest object in the asteroid belt between Mars and Jupiter. For many years, Ceres was considered the smallest dwarf planet in our solar system, a designation that was confirmed by its reclassification in 2006. With a diameter of approximately 950 kilometers, Ceres stands as the largest and most massive body in the asteroid belt. Its size, mass, and unique characteristics make it an intriguing subject of study. As Dawn approached Ceres, scientists eagerly awaited the first detailed images of this mysterious world. The spacecraft's high-resolution cameras began capturing images of Ceres' surface, revealing a complex landscape marked by craters, ridges, and unusual bright spots. The discovery of these bright spots, particularly within a large crater now known as a crater, generated significant excitement and speculation within the scientific community. The bright spots on Ceres appeared unlike anything observed on other asteroids. They seemed to be composed of highly reflective material, possibly salts left behind by sublimated water. This finding hinted at the possibility of cryovolcanism on Ceres, a process where volcanoes erupt with water or briny liquid instead of molten rock. The bright spots, scattered across Ceres' surface, suggested a more dynamic and active world than previously imagined. The bright spots on Ceres, initially thought to be ice patches reflecting sunlight or mineral deposits, were eventually identified as clusters of distinct spots composed primarily of sodium carbonate, a type of salt. This discovery provided crucial insights into Ceres' geological activity and its potential for hosting liquid water. Sodium carbonate's presence suggested that liquid water once existed on or near the surface, allowing these salts to be deposited when the water sublimated. The discovery of bright spots in a crater, including Spot 5, garnered significant attention due to their high reflectivity and periodic hazes observed by the Dawn spacecraft. These hazes were believed to be caused by the sublimation of water, indicating that cryovolcanic activity might still be ongoing or have occurred relatively recently. The presence of multiple bright spots across Ceres further suggested widespread cryovolcanism, highlighting the dwarf planet's dynamic nature. Ceres stands out from other celestial bodies in the asteroid belt due to its unique composition and internal structure. Unlike most asteroids, which are primarily composed of rocky and metallic materials, Ceres exhibits a composition more akin to that of a comet. Its surface is a mix of water ice and hydrated minerals, including clays and carbonates, which give it a less dense structure compared to its rocky neighbors. Ceres's surface is characterized by a combination of water ice and hydrated minerals, which contribute to its distinctive appearance. The presence of water ice suggests that Ceres has a significant amount of this essential substance, which plays a crucial role in its geological processes. The surface layer of Ceres is rocky but porous, with ice and other volatiles trapped within. This icy characteristic is more reminiscent of a comet than a typical asteroid, hinting at a history involving a mixture of rocky and icy materials. Beneath its surface, Ceres reveals even more fascinating aspects of its makeup. The dwarf planet is believed to have a differentiated interior consisting of a muddy mantle and a core. The mantle, which is thought to be rich in water ice, accounts for approximately 50% of Ceres's total volume. Surrounding this mantle is a core that could be composed of denser materials, possibly silicates. The presence of a significant amount of water ice suggests that Ceres may have once harbored liquid water, especially if its core was heated by radioactive decay early in its history. The discovery of ammonia clays on Ceres provides further insights into the dwarf planet's formation and history. Ammonia clays imply that Ceres might have formed in a colder part of the solar system and migrated inward over time. The presence of ammonia can lower the freezing point of water, supporting the existence of subsurface brines. These insights into Ceres's composition and history enhance our understanding of the processes that govern the formation and evolution of icy bodies throughout the solar system. Cryovolcanism is a fascinating and relatively rare geological process, particularly when compared to the more familiar volcanic activity seen on Earth. Unlike traditional volcanoes that erupt molten rock, cryovolcanoes, also known as ice volcanoes, erupt volatiles such as water, ammonia, or methane. These substances can exist as liquids or gases in the extreme cold environments where cryovolcanoes are found. On Ceres, cryovolcanoes function by allowing water packed with dissolved salts to reach the surface. This process leaves behind bright, reflective salt deposits. The most famous of these deposits is located in a crater and is known as Spot 5. This area has garnered significant attention due to its high reflectivity and the periodic hazes observed by the Dawn spacecraft. The hazes observed by Dawn are believed to be caused by the sublimation of water, suggesting that cryovolcanic activity might still be ongoing or have occurred relatively recently. In addition to Spot 5, Ceres hosts several other bright spots, each with its own unique characteristics. These spots are not limited to a single area but are scattered across the dwarf planet's surface, indicating that cryovolcanism may be a widespread phenomenon on Ceres. The dynamic and active nature of Ceres challenges previous assumptions that it was a geologically dead world. Dawn's high-resolution images revealed a surface marked by a variety of craters, each telling a story of the dwarf planet's history. Some craters are relatively shallow and eroded, indicating an old surface that has been subject to numerous impacts over billions of years. Others are more well-preserved, with sharp edges and deep basins, suggesting more recent impacts. Interestingly, the number of craters on Ceres is fewer than initially expected. This discrepancy hints at geological processes that might be renewing the surface and erasing evidence of older impacts. One theory is that Ceres's icy composition allows for a form of cryovolcanic resurfacing, where subsurface materials periodically well up and cover old features. This ongoing geological activity suggests that Ceres is not a static world but one that has been, and possibly still is, dynamically evolving. Further evidence of geological activity on Ceres comes from the observation of fractures, grooves, and troughs crisscrossing its surface. These features indicate that Ceres's crust has experienced significant stress and deformation. Some of the fractures appear relatively young, possibly only a few hundred million years old, suggesting that the crust is still active to some extent. Grooves and troughs likely formed as the crust was stretched and pulled apart, while rows of mountains and compressional ridges indicate areas where the crust was pushed together. The bright spots on Ceres are among the most intriguing findings from the Dawn mission. Initially thought to be ice patches reflecting sunlight, these bright spots were later identified as clusters of sodium carbonate, a type of salt. This discovery has significant implications for understanding Ceres's geological processes and potential habitability. Sodium carbonate deposits on Ceres are not just scientific curiosities. They are key to understanding the dwarf planet's history. Sodium carbonate, also known as soda ash, forms when water containing dissolved salts evaporates. The bright spots, composed primarily of sodium carbonate, suggest that liquid water once existed on or near Ceres's surface. This water would have evaporated over time, leaving behind the bright, reflective salt deposits observed by Dawn. The presence of sodium carbonate also indicates that Ceres experienced significant cryovolcanic activity. The salts, left behind by sublimated water, suggest that there may have been periodic eruptions of briny liquid from beneath the surface. The discovery of these deposits enhances our understanding of the processes that shape icy bodies in the solar system and provides important clues about Ceres's geological history. The potential presence of subsurface water on Ceres is one of the most exciting aspects of the Dawn mission's findings. Water is a fundamental ingredient for life as we know it, and its presence raises intriguing questions about the potential for habitability on Ceres. Radar systems capable of penetrating Ceres's surface could help locate and analyze subsurface water reservoirs. The presence of water ice and the possibility of liquid water beneath the surface make Ceres an intriguing candidate for further exploration. If subsurface oceans exist, they could create stable environments where microbial life might thrive. The thermal history of Ceres, including potential heat sources such as radioactive decay and tidal interactions, is crucial for assessing its habitability. Radioactive decay in Ceres's core could provide a source of internal heat, keeping subsurface reservoirs from freezing completely. Tidal interactions, if Ceres has any moons or experiences gravitational forces from other bodies, could also contribute to the heat needed to maintain liquid water beneath the surface. The Dawn mission has provided a wealth of information about Ceres and demonstrated the potential of ion propulsion technology for deep space exploration. The spacecraft's successful journey and data collection have paved the way for future missions to explore other celestial bodies. Ion propulsion, as demonstrated by the Dawn spacecraft, offers several advantages for deep space missions. Unlike traditional chemical rockets, ion engines provide continuous, efficient thrust, allowing spacecraft to cover vast distances and undertake complex maneuvers. This technology has already been employed in other missions, such as the European Space Agency's Bepi-Colombo mission to Mercury and NASA's DART mission to the Didymos asteroid system. The success of the Dawn mission has also highlighted the importance of advanced propulsion systems in space exploration. As technology continues to evolve, future missions equipped with ion propulsion systems will be able to reach more distant targets, conduct detailed investigations, and contribute to our understanding of the solar system and beyond. The data collected by Dawn has significantly advanced our knowledge of Ceres and the asteroid belt. The findings have implications for asteroid research, planetary defense strategies, and astrobiology. Ceres's unique composition and dynamic geology provide valuable insights into the history and evolution of icy bodies, enhancing our understanding of the solar system's formation. Future missions to Ceres and other celestial bodies will build on the knowledge gained from Dawn. Advanced technologies, such as radar systems for probing beneath surfaces and instruments for detecting trace gases, will offer more definitive answers about the composition and potential habitability of distant worlds. These missions will continue to expand our understanding of the universe and enhance our search for life beyond Earth. As we reflect on the discoveries made by the Dawn mission and look forward to future exploration, it is clear that Ceres holds many secrets waiting to be uncovered. The combination of water, salts, and active geology makes Ceres a compelling subject for further study. By continuing to explore and analyze Ceres and other celestial bodies, we advance our understanding of the universe and enhance our search for extraterrestrial life. In summary, NASA's Dawn mission has not only expanded our knowledge of Ceres, but also demonstrated the potential of advanced propulsion technologies. The discoveries made during this mission have reshaped our understanding of the asteroid belt and provided new insights into the processes governing icy bodies in the solar system. As we continue to explore and study these distant worlds, we move closer to unraveling the mysteries of the cosmos and discovering new frontiers in space exploration.